Maybe I'll get started. Welcome to our Science Revealed session. Since we started this series almost exactly 4 years ago, we've had sessions on data and society, health and environmental justice, UFOs, the concept of nothingness, and the impact of artificial intelligence on all of us. Today, we turn to rather fundamental issues about science and pseudoscience, which bring up many questions such as bias, sources of information, and the criteria to distinguish between the two. Before I hand this off, I do want to thank Jessica Holman, who's here with us to make sure that everything works well, Carol Mullen and Wynn Maloney for their help in organizing this session. And now I'll just turn it over to our moderator, Elise Silva, who's from Pitch Cyber. Elise?
Hi, everybody, and welcome. We're excited to have you here today. So what I will do is introduce each one of the speakers as they present, and we're going to have questions at the very end. So we're not going to have questions in between. There is a question and answer feature that should be on the very bottom of your screen. For some of us, it's under the More option, but for some of us, it's just on the very bottom. So you can submit questions that way, and I will field them and pass them on to the panelists at the end. And yeah, so with that, our first speaker tonight is Melanie Good, who is a teaching associate professor and co-director of undergraduate studies at the Department of Physics and Astronomy at Pitt. Thank you, Melanie.
Thanks, Lisa. Let me just see how to share my screen here, since I do have some slides to show. Oops. Okay. Now let's see if I hit present. Did that go into full screen for everybody?
Yes. Yep, I see it.
Awesome. Well, welcome everyone. I want to talk to you today a little bit about why each one of us might fall for pseudoscience. What is its appeal and how does it suck us in and trap us? I thought a Severance reference here might make a nice title slide because of the juxtaposition of science and pseudoscience that's present in the show. But whether you follow Severance or not is not important to this discussion. So I think I'm going to start by asking a physics question of all of you. So in this photo, which vehicle do you think experienced the larger force of the impact during the crash that took place, the car or the tractor trailer? Well, actually, it's a trap, because Newton's third law tells us that the forces actually had to be equal in magnitude. Isn't that counterintuitive? The scientific truth, as it turns out, doesn't care about our intuition. It cares about reality. Science could even be seen as a trade-off, wherein we seek an accurate explanation for a phenomenon, and we're willing to give up an intuitive explanation for that phenomenon. But that is precisely what makes science vulnerable to perversion at the hands of pseudoscience. Because like other misconceptions, pseudoscience often appeals to our intuition. Could you go on believing that the car pictured here experienced more force than the truck? Sure, the evidence seems to be pictured here. We see more severe damage on the car compared to the truck. And there's another of Newton's laws that helps explain this, of course. Newton's second law tells us that for a given amount of net force, the acceleration is inversely proportional to the mass of the object. So the same amount of force on a small sedan will result in more acceleration than it would be for the truck. And that plus the crumpled design of the car's body helps explain the magnitude of the damage we see on the car. However, if we don't care about writing out some formulas and making calculations, and we simply seek an intuitively satisfying explanation, then we don't have to confront any apparent contradictions with the explanation that there was more force on the car. It's not accurate to say this, but it is intuitive. And that's how pseudoscience often preys on us. It appeals to our intuition, which can be shaped by political, social, religious, and other factors, along with our everyday experience. And in the process of offering us an intuitive explanation, pseudoscience often dodges critical scrutiny or finds a way to explain away evidence against it. Neil deGrasse Tyson is a well-known scientist and science communicator, and he is quoted as saying, "The good thing about science is that it's true whether or not you believe it." In saying this, Neil deGrasse Tyson isn't just defining what science does, he's also revealing what it culturally prioritizes and selects for. Science prioritizes truth above belief and intuition, and it invites scrutiny to weed out our mistakes. So while individual scientists carry human trappings and flaws, the process of science is constructed to be iterative and as self-correcting as possible. As a consequence, its conclusions can change as better evidence comes to light, but the truth that is revealed may or may not resonate with a person's biases and beliefs. And particularly pesky are biases we may not even realize we have. In fact, we all have cognitive biases that hinder us from objectivity and make us more vulnerable to belief in pseudoscience. And I'd like to spend some time talking about a few examples of those. So this won't be, we don't have time for an exhaustive list of all cognitive biases here, but I want to highlight some of the ways in which, along with offering an intuitive explanation, pseudoscience can also draw us in due to biases we may not even be aware that we have. So the first category of biases I'd like to highlight are anchoring biases, which cause a tendency for us to rely too heavily on one anchor or piece of information. Some specific examples of anchoring bias include the law of the instrument. In this bias, if you have a tool such as a hammer, everything looks like something to apply that tool to. In other words, everything looks like a nail if you're familiar with a hammer, even if it's actually a screw and it might be better to use a screwdriver. For instance, part of what felt so intuitive when we tried to explain the car crash earlier has to do with our mental framework of forces. Maybe we're used to thinking that more force equals more effect. Another anchoring bias is conservatism bias. This is when we may not adjust our beliefs sufficiently in the light of new evidence. You might ask yourself, will you remember after this webinar how Newton's third law applies to the car crash? Or will the more intuitive explanation be the one that sticks? It's hard. Our misconceptions are like pseudoscience in that they are resilient to evidence to the contrary. Our beliefs aren't simply penciled in and easy to erase. They're more often like permanent ink, where it's harder to change them. So even if we see evidence against some pseudoscientific claim, it may be hard to revise our belief if we've already adopted it. Another category of cognitive bias is apophenia, which is the tendency to perceive meaningful connections between unrelated events. Some specific types of apophenia include the illusory correlation, which is a tendency to inaccurately perceive relationships between two unrelated events. And another kind is pareidolia, which is a tendency to perceive vague or random sight or sound inputs as something meaningful. You see an example of that pictured here. The top image was taken in 1976 by the Viking 2 during a flyby of Mars. It's fairly low resolution, and the way the shadows fell when the image was taken made it look to a lot of people much like a human face. This led to a lot of wild speculations about intelligent Martian civilization. In 1998, more detailed, higher resolution photos began to be taken, and in 2001, the bottom image made it abundantly clear that this particular rock was nothing more than that, a rock, not a human face. But it's easy to see how pareidolia may have caused us to see a human face in the top image. Of course, in this case, the preconceptions about intelligent life on Mars also created an expectation that highlights the next kind of bias I'll talk about, and that is confirmation bias. Confirmation bias is a tendency to remember things that appear to confirm your expectations. This is a potent way in which fortune telling appears to work. A prediction about your future is often worded in a vague way to begin with that helps allow confirmation bias to kick in because your expectations are ill-defined. Take this fortune, for example. It's telling us to be patient and implying that it takes time to achieve things. That's pretty generic. You might read this and go about your day as usual, but then if any one event happens that reflects success from patience and hard work, you might interpret it as the fortune coming true. And it could mean almost anything to anyone. Maybe you got a raise at work. Maybe your kids finally picked up after themselves. Or maybe you had a great interaction with a cashier after waiting in line a long time at the grocery store. There are countless ways in which this fortune could be seen to be coming true and confirming our expectations. Yet another category of cognitive biases are egocentric biases, in which we focus too much on our own perspective. For instance, astrology offers descriptions of the type of person you might be based on your astrological sign, and your tendency to see yourself in those personality traits is an example of the Barnum effect, which is a type of egocentric bias. The false consensus effect is also considered to be a form of egocentric bias, but it has a social element to it as well that comes about because of the way we tend to surround ourselves with like-minded individuals. You've likely heard the term echo chamber before. That's where this is going. And I could talk about additional cognitive biases, but again, we are time limited here. And I think this gives us a sampling that is enough to highlight some of the common biases that could help explain why we might fall for pseudoscience. When it comes to belief in pseudoscience, cognitive biases often work together with those intuitively satisfying explanations. After all, when we find an explanation that fits with our intuition, it can resonate with us in a way that makes us feel as though we have found something out about nature. It can give us that light bulb, aha moment that scientists often talk about as a fulfilling aspect of what they do. But in the case of pseudoscience, the aha moment is just an illusion. The good news is, if we are willing to be honest with ourselves and create space to pause before accepting an intuitive explanation, and if we can be self-aware of the cognitive biases we might have, then we might be successful in uncovering pseudoscience for what it is. But it helps to know what signs to look for. This is not meant to be a comprehensive checklist, nor does it offer any guarantees, but here are some telltale signs of pseudoscience. I'll just give you a second to look at those. And I will close by saying that science, in contrast to pseudoscience, invites scrutiny to help it self-correct in its quest for truth. And in my view, science is not only a richer and more inspiring explanation of nature, it also is the best tool we've devised as a species to help us understand the real way nature works. And with such an understanding, rather than fall victim to superstition and pseudoscience, we can harness the power of science to appreciate and understand fascinating natural phenomena. All right. Thank you, everyone.
Thank you, Melanie. That was great. I'm going to introduce our next speaker, but just remind the audience that you can ask questions and they'll come directly to me, and we will ask all of our questions at the end. So the question and answer feature is at the bottom of your screen. I'm going to now introduce our second speaker, Eric Swanson, who is a professor in the Dietrich School's Department of Physics and Astronomy, and a colleague of Melanie here at Pitt.
Hi, thanks and for the introduction and good evening, everyone. Uh, my plan is to give you some historical examples of pseudoscience, and then we can develop from there and discuss and explore how this phenomenon comes about and how you can detect it, as Melanie was talking about. So I hope my slides are displaying now, and I'll move ahead. So I'm going to start with this image here that shows the meeting of a river and a freshwater system. And there's a boundary between them. And the boundary is pretty obvious. And we like to pretend that there's a pretty clear boundary between science and pseudoscience. It turns out it's pretty tough to define science, let alone pseudoscience. Science is a human activity, and because of that, it's subject to all the frailties of humanity and makes it difficult to define. In fact, one of the things I want to point out is that these can shade into each other. And that's one of the reasons detecting pseudoscience is difficult. So I'll start with a historical example of that. This is a picture of an alchemist. And for several centuries, alchemy was regarded as science. It was only in the 1600s that people started to regard it as having a flavor of the occult, and it fell out of fashion. It was no longer considered science. And then, strangely enough, starting in the 1930s, it's come back. We don't call it alchemy anymore. It's called nuclear physics now, but we actually can convert lead into gold if we work hard enough. So it has gone from science to not science and back to science again. I like to point out to my students when I talk about this stuff that, as Melanie said, science tends to be self-correcting. It's whereas pseudoscience isn't self-correcting. And in fact, it can change, the content of pseudoscience can change with where you are and when you are. And there are fundamental symmetries of nature that say that where you do an experiment or when you do an experiment, the results of your experiment are going to be the same, regardless of when or where you do your experiments. This is not true of pseudoscience. And this slide shows some examples of when I was much younger, the current pseudoscience of the day. So chariots of the gods and things about pyramids and biorhythms. And I ask my students about this now, and no one knows what any of this is. So it's not, something that continues in time. There are exceptions, of course. This is a famous one. This is meant to be astrology, which has been around for thousands of years. So it's got something that resonates with people, this idea that the stars control our lives to some extent. This is another example I like to give. This is a frontispiece of a pamphlet that was published in Paris in the late 1700s. And there's a lot to unpack in this. I can't actually do it all, but I can start. So on the left here is none other than Benjamin Franklin, and he's striding forward carrying a report of the commissionaires that says, what had happened was the King of France had ordered the commission to be formed to investigate the workings of an Austrian doctor who was living in Paris, who's being carted off by witches to the upper right there on that broom. And that doctor is Franz Mesmer. And Mesmer comes down to us today through the English word mesmerize. And Mesmer was convinced, he had convinced himself that he had powers to control magnets. He could control magnetic fields. And with that control, he was able to cure the ills of people. The people he tended to cure in his clinic tended to be the wealthy young daughters of the aristocracy, and they got wind of this and got upset and raised the issue with the king, and this commission was formed. And they actually performed some quite clever experiments to prove that what he was doing was all suggestion and placebo effect, and he was, subsequently run out of the city. Here's another example dating from a similar time. It involves this man on the left, Samuel Hahnemann. Hahnemann is the person who invented homeopathy. So, as you're probably aware, homeopathy is still a thing now. So it's been around for hundreds of years. He was doing science, even though this is regarded as not scientific now. It's regarded as pseudoscience. So he was a doctor. At that era, they had things like bloodletting and, strange concoctions and drilling holes in people's heads and things like this to effect cures. And he, for reasons I don't have time to get into, got the idea that if you expose people to the thing that made them sick, it would make them less sick. And he tried it out on himself and it just made him sick. So he diluted the thing he was exposing himself to more and more until he didn't feel sick. And in fact, this was an advance. He tested it and it was an improvement over current treatments. For reasons that we now understand is that the treatments were so bad that it was better to do nothing. And so he was doing science and determined that using these methods help people. So the thing on the right here is a container of arnica montana. It always looks quite medical. It says, don't take too many of these and consult your doctor and all of this sort of stuff, all of which is meaningless. And it's meaningless for a reason that's easy to discern. So unlike the alchemy business or astrology, this one's easy. So this C, you see it says 200C there. What C means is they diluted the active ingredient by a factor of 100. And 2C means that they do that twice. So they diluted it by a factor of 100 times 100, which is 10,000. This particular product has a dilution of 200C. So I'm going to do this in reverse. If I take a single particle and multiply it by a factor of 100, so I have 100, and then do it again, so I get another factor of 100, and do that 200C times, what I would get is this number, 1 followed by 120 zeros, number of universes of particles. So in other words, this dilution factor is so large that there can be no active ingredients whatsoever in this. In fact, it would only have to be 40C to get down to 0 active ingredients. In other words, the pill is a sugar pill. So what they're relying on in modern times is the placebo effect. So this is an easy example of pseudoscience. This is another historical one that I like to talk about. It starts with Galvani. So this another scientist who's given his name to an English word, galvanism, or galvanic action, and so on. He did the famous frog leg experiment. So these probably was going to be his dinner later in the evening, but he had some frog legs, and he had a piece of copper and a piece of zinc. Those are the two pieces of metal there, and he touched the frog with these two pieces of metal, and the leg twitched. And what he thought he had discovered was something about life, that somehow electricity, so these two different metals cause electrons to flow, we understand now, something about electricity was related to life. In other words, he had imbued this leg with life. And that idea has stuck with us to this day. So remember also that Mesmer was fascinated with magnets. So both electricity and magnetism come down to us today as something that people give occult properties to. Now, it turns out there was another Italian scientist. Luigi was in Milan, and there was Alessandro Volta was in Como, not very far from Milan, at the same time. And he thought, oh, my colleague Luigi's wrong. What he's actually done is discovered what happens when you mix salty water with copper and zinc. And he invented the battery. The voltaic pile is just copper and zinc with salty water, and that makes a battery. And of course, he was right. So this idea, as I mentioned, comes down to us today. It was followed up pretty rapidly by this famous novel written by Mary Shelley, where Dr. Frankenstein creates his monster and he has to imbue it with life. How does he do it? Electricity, of course. In the movie, it's with lightning being captured and channeled into his monster. There are all kinds of modern examples of this. Cell phones work with radio waves. Radio waves are, a phenomenon of electricity and magnetism. And there are people who think that your cell phones are killing you. The article down here at the bottom is maybe cell phones are killing the honeybee. I thought this was a joke when I first saw it, but apparently a reasonable number of people think this is true. If at the upper right there, if you go into quite a few drugstores, you will find products like these. These are magnetic bracelets. And somehow the fact that the bracelet is magnetized is meant to help you deal with arthritis or diabetes or something like that. And all of this is, of course, nonsense. So these things are all pseudoscience. So a lot of this stuff starts with legitimate sources, and quite often it's scientists who are doing not very good science or science that gets subsequently misinterpreted, that gives rise to pseudoscientific ideas. And I have hundreds of examples of this sort of stuff. I just picked this one at random. This is an actual research published by actual researchers in an actual journal talking about how ants can detect earthquakes, which, honestly doesn't seem very plausible. This slide talks about the measles outbreak. So this has to do with the modern version of the anti-vax conspiracy theory. So with things shading into each other, conspiracy theory and pseudoscience tend to shade into each other as well. It was started, the modern version of this was started by a very, so poor that it caused legal problems study by a man named Andrew Wakefield. And it was picked, he claimed that the MMR vaccine was causing horrible brain trauma in children with a very bad study. And that was subsequently picked up by the media because it's very dramatic, and then got distorted into it's causing autism, which is a natural outcome of some of the biases that Melanie was talking about. And we now know the result is measles was declared eliminated in the United States 20 years ago, and now it appears to be back. And I'll finish with just a modern example of this stuff. So this is just from a few days ago, where our illustrious new Director of Health and Human Services, RFK, is starting to make misleading claims about many things. One of them includes the measles vaccine causing health damage. He referred to an article in his interview, and I thought I should just do a little bit of research. So I want to show you what happens if you dig a little bit when you see these claims. So the article he was referring to is fairly easy to find. It was this one. And if you look at the top there, it's got that leader that all looks pretty legit. It seems like it says it's a research article. It looks legit. It turns out this is not a research journal. This is a blog that's made to look like a research journal. If you continue, it looks like an actual study. Then you look at the author and you Google him and you find him very quickly. It's Anthony Mawson, who's the president and founder of the Chalfont Research Institute. And in fact, his address is given as the Chalfont Research Institute. So you look that up on the internet and you find out no information whatsoever. This is not actually a research institute. The only thing you can find about it is that it was declared as a charity at some point, so it has to file tax returns, and you can see that it actually exists as an entity, but other than that, it has no presence at all. In fact, if you scroll a bit down, you see that the president of it is in fact the author who claims it as his place of work, and he pays himself a salary out of this thing. Okay, so I'll finish up there. Some of the messages I want to get across, it can be difficult to perceive pseudoscience, to distinguish it from science, because it does often shade in so much into actual science. Science that's been sort of abused or done poorly or misinterpreted. Sometimes it's easy if you violate standard laws of physics, it's pretty obvious. It does prey on our flaws. It is everywhere. Every day I see examples of pseudoscientific thought in the news. And it's damaging. You could argue, oh, it doesn't matter if people believe in chemtrails or so on. But I think if you're making decisions about how to act based on information which isn't true, inevitably it leads to bad outcomes. It is possible to deal with it, to develop a skill set, what I call an anti-BS skill set. It is possible to do that. Part of it is internalizing the list that Dr. Good showed you just a moment ago. And as usual, a healthy and even-handed dose of skepticism and self-awareness can take you a long way in addressing these issues of pseudoscience. Okay, I'll stop there and turn it back to our host.
Thank you. Thank you so very much. Our next presenter is Nicole Heller, the curator of Anthropocene Studies at the Carnegie Museum of Natural History. Take it away.
All right. Great. Let me see if I can get my screen going. Let's see here. Do you see my presentation properly?
Yes. Yes,
Great.
we do.
Okay. Hi. It's nice to be with you all here tonight, talking about this important topic. My name is Nicole Heller, and I'm an ecologist by training, but I work a lot on helping publics understand and think about topics that are important to affecting our ecology, which climate change is one of them. So I've spent a lot of time studying climate change over my career and encountering a lot of pseudoscience as I've tried to work with publics to understand these issues. So I'm going to just talk a little bit about some of these characteristics of kind of how pseudoscience is used as a deliberate tool to slow action on political issues. That last example with the vaccine and Kennedy, actually, there's a lot of similar tactics that I think Kennedy is beginning to use that have been used by climate science, not by climate scientists, but other kinds of experts trying to sow doubt about climate change. So the lessons from climate are really important for evaluating all kinds of issues we're confronting in our society. So a question I get asked a lot in talks, or just kind of the way we frame climate change, as it's a scientific topic, but it gets framed a lot as this question: do you believe in climate change? And it always frustrates me when I get this question, because it really isn't the right question to be asking about a science topic at all, right? It's not a matter of what I personally believe or feel or intuit, but what is the evidence and what does the consensus say about that evidence? And so really at this point, this question is really off base in a lot of ways, because there's just a mountain of evidence to support the idea of human-caused climate change. And I would argue that there's probably more consensus and evidence about human-caused climate change than almost any other scientific issue. And it's kind of an incredible body of work to look at how has this climate consensus developed? How have scientists collaborated all over the world to create this understanding that we have? And the scrutiny that they've really applied to this work. So the little graphs I'm showing here, this cartoon, it's really interesting, the staying power of these myths or concerns about climate change. They really don't go away, even though they've been discredited for so long. And part of that is because there's the science community and what's understood and what's still under debate within the science community. And then there's kind of the public understanding and the media journalistic presentation. And there's a huge gap, and people call this like the consensus gap, which you can see this graph here where, it's been commonly cited for at least a decade that about 97% of climate scientists agree on the fundamentals of climate science. And yet, when you ask the public how much certainty is there about climate change, you tend to get, like this graph says here, 55%. So just a big gap between the science community's understanding of the science and the consensus and the public, which is really driven by media and an active kind of disinformation campaign that relies on a lot of pseudoscience to confuse people and keep them confused fundamentally. I wanted to show this little timeline about the Intergovernmental Panel on Climate Change and the assessment reports that they've been doing for the past 30 years, because as Melanie was talking about, the way that science is iterative and self-correcting and collaborative and has this peer review, I think this process that has been driving the Intergovernmental Panel on Climate Change has been using really demonstrates this, and really is how you can sort of trust this science. If you look over the course of the 30 years, you see the certainty around the fundamental claim of the relationship between warming and human causation just getting stronger and stronger. And so you don't need to read all of this, but like in 1990, the report said there was uncertainty right at that time. And it says the unequivocal detection of enhanced greenhouse effect from observations is not likely for a decade or more. So there's sort of like, we see this science, but we can't quite demonstrate it yet. But even by 1995, they say the balance of evidence suggests a discernible influence on climate. And kind of fast forward through multiple assessments to 2023, the AR6, the sixth assessment, the statement and the report, the main statement is human activities, principally through the emissions of greenhouse gases, have unequivocally caused global warming, with global surface temperature reaching 1.1 degrees Celsius above 1850 to 1900 in 2011 to 2020, right? So by this point, there is certainty, absolute certainty, through these decades of scrutiny and experimentation and modeling and this huge field of climate science that has grown up. And in a way, when you think about this, I was thinking about this question at the beginning of the talk about how do we get armed to be able to discern pseudoscience from science? In a way, with climate science, we're kind of lucky because all these scientists are doing that work for us. We don't have to discern the evidence. Thousands of scientists are working together to do that. Yeah, to that point, if you look at, here's a graph just showing where the IPCC AR6 authors come from. They come from around the world. And overall, they have been over 3,000 participating scientists who've worked together to develop this and do this peer review process together and assess the science and try to stand up to political processes that want the science to maybe, the findings are not, they're inconvenient, right? As Al Gore famously said. And so it's really takes a lot of bravery and courage for these scientists to do this work and keep trying to stick to what does the science tell us? Where is there certainty and where is there isn't certainty? And it's an incredible, I think these reports are really fascinating to look at even the changing language around certainty that's been developed over the course of this field. So despite all this mountains of evidence, there are common myths about climate change that continue to circulate today. And I experience this every day in my work here in Western Pennsylvania. There's a lot of, while overall the majority of people understand that climate change is human caused, there's still a lot of people who are uncertain. And when you talk to them about this, they often say things like, well, it's natural. Actually, the Natural History Museum shows us that it's natural. You can see climate change through history. Or, yeah, the climate is changing, but it's not human caused. And the scientists don't really agree. So these myths or things continue to circulate. And this book that I have found very important and interesting in my own understanding is a book published, I think, around 2010 called Merchants of Doubt by two historians, Naomi Oreskes and Eric Conway. And they really show that this misunderstanding and these pseudoscience, that's circulating is not by accident, that it's a tactic. So the idea here is that climate change is not a scientific debate. It's a political debate that's been made to look like a scientific debate. And that has been purposefully done because if the science is still debatable, then policy responses can wait, right? Policy shouldn't get out ahead of the science. So as long as we make sure the science is presented in a way that seems uncertain, then we don't need to act on this science. And this book does a great job of showing all of these different tactics that are used, like using fake experts, publishing reports that aren't peer reviewed, but making them look like they are real, cherry picking, having a few minority scientists who are made to look like they're the majority, and then attack and discredit. And I think this is one of the really interesting things that climate scientists have to suffer. When they do publish strong results, they get attacked. Even these days like death threats, and people have to go into lockdown. And just for example, Naomi Oreskes, Senator Jim Inhofe, after she published her book, really villainized her and said that she was part of a global conspiracy to bring down global capitalism, and she had death threats and had to hide out. So it's really intense the way that this doubt is sowed, and the way that the expertise gets really attacked as part of this methodology. So just to take on one topic, one of the main ones, this question of, is it natural? This graph that I'm showing here is a really wonderful and persuasive demonstration of how scientists have been able to conclude that that climate change is not the result of natural causes. And what this graph is basically showing is that if you follow the blue line, the light blue line, that's the observed temperature change over the last 150 years or so. The red line, and then the dark blue line, is showing the modeled temperature we expect when you include natural and human-caused factors like fossil fuel contributions. And you can see that really great match between the observed temperature and the modeled temperature. But then if you model climate without the human causes and only the natural causes like solar, volcanic, and other kinds of variability, you see that the natural causes just cannot predict the observed variation. So the evidence here has gotten really strong. There are also so-called 10 or more other human fingerprints, all these ways that scientists have been able to conclusively demonstrate the human cause. And so as these pseudoscience and myths circulate, the scientific community responds to kind of double down in figuring out more and more ways to demonstrate how the science is real. I don't want to go too much into this, but this is just an example from Oreskes' book of how that myth about it being the sun really got started. And there's the George Marshall Institute, was founded by these three physicists in 1984, kind of with these guys basically developed this nonprofit in order to try to kind of review scientific evidence and influence policy. They first were working on Cold War issues, and then they shifted in 1989 with the fall of the Berlin Wall. They shifted to what they called environmental alarmism, or what they called like a green tree with red roots, and really concerned around the climate scientists and environmental scientists being a sort of like socialist or anti-market agenda. And so at this time, just one clear example of the way that this pseudoscience worked is they circulated a white paper that blamed global warming on the sun. And basically what they did is cherry pick data that had been presented in a peer-reviewed article by a climate scientist, James Hansen. They cherry picked it, and they only used the part. I'm kind of showing this graphic. They didn't use the whole graph. They just cut the top part of that graph and included it in this white paper that suggested CO2 really couldn't predict climate change, and that it was solar that was a better predictor. They circulated this. It was widely refuted by the IPCC and other peer-reviewed stuff, but it didn't really matter because the report was circulating. It had the effect it needed to have in political circles, and it's credited, this Marshall report is credited as contributing to the US government's failure to restrict fossil fuels in the 90s during those early climate conferences. Just briefly, solar and wind is bad for birds is a major one circulating right now, a lot here in Western Pennsylvania. And we've done a lot of meetings to try to help people. We get a lot of calls at the museum, people freaked out about solar or wind and its effect on birds. And there really isn't strong evidence that this is, that climate change is a much bigger threat to bird populations than is clean energy. And there's really very little evidence about clean energy being a big problem, as you can see with this graph I'm showing down here relative to other issues like cats, it's not a big impact. And if you look at all the bird organizations or natural organizations like Nature Conservancy, they're all much more concerned. They're all pro clean energy. But this topic is circulating all throughout our communities and really slowing clean energy development because people are freaked out about it. So I just quickly to finish up, there's tons of information about the pseudoscience and myths around climate science. These are just some of the sites that have whole projects that developed to refute these myths. I think Skeptical Science has about 250 that they refute. And I guess I'll just finish with this. Climate denialism has been an effective tool distracting us from key questions and so we need to stop asking this question, do you believe in climate change, and really focus on the questions we need to be asking, like how is our climate changing and how can we prepare our communities? And finally, just the point that when you stand up for climate science, you really are standing on a mountain of evidence. So no one should ever feel like any sort of concern about defending climate science. So thank you very much. And I'll end there.
Thank you. Thank you so very much.
Let me stop sharing. Whoops. Sorry.
All right. Our next, our final presenter is John D. Norton, who is a distinguished professor of history and philosophy of science at Pitt. We're excited to hear from you.
Okay, delighted to be here. Let me see if I can get my screen up there. Okay, and at this point you should see full screen.
We do.
Yes? Okay, perfect. All right, so let me get started. I'm a philosopher of science, and in my community, the question of what distinguishes good science from bad science is something we talk about a lot. Of all of those discussions, only one of the ideas seems to have filtered out into broad understanding in the larger population, and that's Karl Popper's idea of falsifiability. I really only have one message for you tonight, and that message is simply this: it's a bad criterion. And when you take it seriously, it ends up causing more trouble than it does good. So I'll try and make good on that on that claim. So let me see if I can go. Okay, here we go. So here's Karl Popper. The idea is that a good science is going to be making predictions that can fail under some conceivable circumstances. The fact that the science can fail in its predictions, the predictions will not match what we experience, that's the property of falsifiability. And that is the property that Karl Popper insists distinguishes or demarcates science from non-science. So the idea looks something like this. Here's science, and over here is non-science. And you look for the property of falsifiability. If you find it in some body of work, then it's science. It gets an award, something like a purebred dog at a dog show gets a nice award. And if it's not falsifiable, then it's non-science. It's the mutt, and it can be forgotten about. So my message is that that's the wrong criterion. So you want to know what is the right criterion? Well, in my view, the right criterion is the one that's been talked about by the earlier panelists here. What distinguishes better science from worse science is simply the strength of evidential support. That's really all that matters. Ask, what's the evidence for that particular claim? If it's strong, you're dealing with good science, and if it's weak, you're not dealing with good science. So you get, as I think Eric pointed out, you get a real continuum here of support. We can go all the way from the best supported science and bleed off into something that's very poorly supported. You know, where does science end and something else start? It doesn't really matter. All that matters is how well supported are the ideas that we're dealing with. And so you can you can find that a science or proposal that starts at one point here can migrate around according to how the evidence rises and falls. The atomic hypothesis was something that was very poorly supported for a long time, and then eventually in the 19th and early 20th century, got strong support. Now, determining that support is not something that can be done easily by simple criteria, something where you just check a box and bang, now you know this is science, this is not science. It's much too easy. And when you have an oversimplified criterion like that, if you apply it seriously, you get all sorts of trouble. And that's what I want to tell you about, some of the trouble that arises. The first is that falsifiability is something that can be attained far too cheaply. All sorts of bogus ideas can be given the label of science because they are indeed falsifiable. Give you a couple of examples here. I hope we all agree that by the 19th century, the idea of a flat Earth was not to be taken seriously by anyone in science. We've, for several hundred years, had a very successful heliocentric model of the universe. We had geodesy going back for a long time, measuring distances, yet in the over the surface of the Earth. Yet in the 19th century, a number of writers came to advocate very seriously and very powerfully for a flat Earth. This is a map that's produced by Gleason towards the end of the 19th century. And you can already see on the map that geodesy, just measuring distances on the Earth, is going to be enough to falsify this. The circumference of the equator is going to be something like half the circumference of the outermost edge, which is the so-called ice wall that walls off Antarctica. It's just a matter of sailors reporting distances. It's eminently falsifiable. Are we to call that science? I certainly hope not. Here's another example. Dowsing, again, has a long history going back to the 15th or 16th century. The idea is that if you have a sensitive twig, you can determine minerals and then ultimately where water is underground. By the beginning of the 20th century, dowsing had been so completely discredited, there was no plausible physical mechanism through which the twig and the water could connect. We'd busted the idea that that the dowsers were cheating. In fact, they were kidding themselves with psychological effects. Nonetheless, proponents of dowsers continued, and they said, no, it works because of a parapsychological effect, something like telepathy or ESP. Well, I hope you can recognize that as really bogus science, but it's falsifiable. You can do the experiments, and the experiments were done, and they all came out to be negative. Once again, the criterion of falsifiability is giving us the wrong result, asking if the evidence is giving us a good result. So is there any harm done by this? Isn't it just funny and laughable? Well, no, there's a really serious case of harm here. Evolutionary theory has been and continues to be under threat from creationists. They have theological motivations for wanting to say that all the various species came into being some few thousand years ago in a divine act. Is this falsified? Is this doctrine of creationism falsifiable? Yes, eminently so. The scientific creationists themselves have been able to specify exactly the conditions under which they would be falsified. They talk a lot about the idea of irreducible complexity, and I've given a quote here on the screen of a way that they would accept falsification. So it's falsifiable. Okay. That's the first difficulty. It lets in too much. And the second difficulty is that if you take falsifiability too seriously, you start to distort what counts as good science. So let me give you a couple of examples. Modern cosmology is based on the so-called cosmological principle. It says that the universe on the larger scale represents a uniform aspect. There are, of course, local homogeneities in matter distribution, but on the larger scale, everything evens out. This assumption is fundamental to deriving the space-time structures that we base modern cosmology on. Now, the difficulty with the cosmological principle is we actually see a lot of inhomogeneities. And so one of the questions that then comes up is, if we keep expanding the volume of space that's involved, will we eventually get to some sort of uniformity? well, we can just keep going and going and going. It doesn't matter how much inhomogeneity you see locally. You can always say that a further expansion will lead us to homogeneity and the cosmological principle. That's just one example. It's a fairly striking example and well known. But once you start looking for examples that are more hidden, they are everywhere in the science. So here's a periodic table of the elements. Direct your attention to nitrogen and oxygen. Is there an element, chemical element, that sits in between nitrogen and oxygen and would belong there in the periodic table? Now, if you know anything about how the periodic table is being constructed, there's no credible scientific possibility for this to happen. The quantum mechanical construction of these elements has been known since roughly the 1920s. And if you take the science at all seriously, it's simply impossible. But who knows? Right? If you keep looking and keep investigating, you might just find something somewhere that would credibly live between nitrogen and oxygen in the table. It is unfalsifiable, but the evidence speaks massively against it. Once again, just looking for the evidence gives us the right result. Looking for what's falsifiable gives us the wrong result. Does it matter? Yes, I'm afraid it does matter. It matters in the evolution case rather badly. It has distorted our judgments of how good science is done. The so-called historical sciences are ones that depend on drawing evidence from the past and inferring what that evidence tells us. Evolutionary theory, geology, archaeology work that way. The basis of evolutionary theory lies heavily in inducing what we can learn from past evidence. Under pressure from the creationists who keep insisting that, oh, you aren't making predictions, you're not falsifiable, you're not science. Under pressure from that, they have started to talk in ways that I think distort the evidential basis of science. I've noticed to my despair in this rather otherwise wonderful response from the National Academy of Science to creationism, they're starting to define science as something that makes falsifiable predictions, which is just not the way that evolutionary theory has worked, and they're scrambling about desperately to find falsifiable predictions that are coming out of evolutionary theory. The whole debate has been distorted by taking falsifiability too seriously. Well, that's pretty much all I have for you. There are further things that I can talk to you about. I'll just mention what they are in case you're interested. All is not lost with falsifiability. I'll just mention here briefly that if a theory turns out not to be falsifiable, that is a warning that there's something wrong with the evidential basis for the science, something we can talk about more. There's certain considerations to look into. There's also a neat historical story. Popper did not offer falsifiability as an addition to strength of evidential support, but as an alternative. He actually denied that there was such a thing as reliable inductive evidence, and how that came about is an interesting story. And then finally, I can tell you a bit about the reaction to Popper's work amongst other traditions in philosophy of science. So if you're interested in what I've had to say so far, I put some effort into writing up something that you can read that has more details. There's a section of my website that I call the goodies page. It just has stuff that I put up because I find it interesting to write about. If you scroll down through this list here, you'll eventually come to this one, Why Falsifiability Does Not Demarcate Science from Pseudoscience. I'd recommend you look at it. I've tried to present things in a clear and simple manner as I possibly can. Here's the URL, but if you simply Google my name and goodies, you'll get there pretty easily. And with that, I'll finish. I think I'm only a minute or two over, so thank you very much.
Thank you to all of our panelists. Yeah, round of applause, digital round of applause for everyone. All right, now comes the very exciting time where we can have a conversation together. Just a reminder that you can submit questions using the question and answer feature at the bottom of your screen, and I have several here. And I'm going to start us off just by kind of recapping a few things I think we heard. We heard Dr. Melanie Good talking about like signs that something is science or pseudoscience and the cognitive biases that affect how we experience scientific information. Dr. Eric Swanson gave us examples of pseudoscience. Dr. Nicole Heller talked about the intentions or motivations behind pseudoscience, like as a phenomenon and how it circulates in the information ecosystem. And finally, Dr. John Norton talked us through some discussions of like evaluative methods when it comes from distinguishing real from fake. So I have a question, and it actually relates to something that was typed here in the question and answer. My question is, we talked a lot about like how you evaluate science when it's in front of you, like as a piece of information. But what about analyzing how that information got to you? That's a question of like information ecosystems or information pathways. How do we find good scientific information and understand that, recognizing that not everybody can be an expert, right? Not everybody can be a scientist. So I think it's quite easy to say, don't get your information from social media, but not everybody is going to have the same level of information skills that an expert would. So I'm going to read a question here as well. That I think that puts this out there. It's a question and a comment. So underpinning the problem of belief in pseudoscience is what seems to be a fundamental information science problem. And my background's in information science, so I do love this question. What has become the most popular method to search for information is something based on internet searches, including social media sources. But as far as I'm aware, education systems have not formalized a core skill or discipline how to both search for information and how to discern fact from non-fact. Essentially, students from an early age do not appear to be taught how to become effective information scientists at a practical, usable level. So this would be called information literacy, which is an applied science, and it depends on one's discipline, right? So the question is, is there something that needs to be a requirement in this age of information or misinformation? And I would expand that to say, how do you teach your students or people in your lives how to access information, like the information pathway question? So a general question.
I can jump in if no one wants to start. It's a great point. There's a flood of information and it's just going to get bigger and bigger, and people need to know how to assess it. I hope that at high school, people are taught how to accumulate and assess evidence. I do remember when I took in my history course, I was, we were made aware of this, that this was an issue, that you need to be aware of what your sources are. In terms of how we respond as professors teaching young adults, quite often it's not taught. It's not even discussed. I am an exception in that I teach a course where this is part of the course, where part of the material is assessing the information that's flowing past you every day. I don't know how that works in other courses. We don't have time in physics. I know that. I don't know how that works in other departments.
I'll just echo and say that, yeah, this is definitely an issue. And I think one of the things that makes it even more tricky is the way that the issue has evolved with time. And, I think we probably all here can remember when the word, did you get your information from Wikipedia, was a question that would have been disparaging. But these days, Wikipedia is well enough vetted that it's oftentimes a good starting point. And, so I would encourage, students to look at that as a starting point and then go to the primary sources that are listed at the bottom of Wikipedia. Or if they're seeing something in the popular media, some study that was done and some scientific result that was claimed, it's often sensationalized. And so it's often informative to click to the original source. So I think the idea of like going to original sources can be beneficial. But as to whether or not that message is getting to students from a young enough age, I'm not entirely certain.
Go ahead, John.
Oh, I think this is a very serious problem, but oddly, I'm rather optimistic. Once upon a time, before the internet, getting information was hard. And if you had someone that was feeding you false information, if you wanted to bust them, you'd have to go to a library, find a good book. That's no longer the case. If you have a critical mindset and you hear some crazy conspiracy theory, all the good information is at your fingertips with a mouse click. It's actually easier now to be well informed and to be able to distinguish bad work from good work than it ever has been in the past. And we know how to do that. Anyone who has some kind of understanding of how our system works, our system of science works, will know that referee journals are a great source. They'll know that certain types of encyclopedias are great sources. And you learn pretty quickly where the good places and where the bad places, and you learn pretty quickly to cross-reference things. If something is a wild, bad conspiracy theory, you only need to put in, the keywords describing it, and is this a conspiracy theory into Google, and you'll have a mass of people debunking it. So, I'm thinking the sources are there and it can go very well. How we get people to do that, that's a harder question.
Do any other panelists have?
Yeah, this is Nicole. I'll just say, I mean, I think it's a great question, and it's a bit overwhelming. I mean, I know I personally experience just so much data. It's hard to know what's good data or not data when you're busy and you're reading lots of things on the internet. One thing that I worry a little bit about too is even peer-reviewed journals seem to be exploding, at least in my field in sustainability and conservation. And there's just so many of them that it's hard to discern which is a good peer-reviewed journal from just a peer-reviewed journal at this moment, because it's making publishing quite easy. I think the bar to publish is becoming lower with the plethora of journals that are out there, these online journals being published all over the world. And probably the peer review is going to suffer as well because of the volume and of the journals and the volume of. So that is something that I haven't thought a lot about, but I've noticed this sometimes with student work is like they're just using sources that look good, but like, what is the quality of those sources in this environment that we're in?
Yeah, thank you all for weighing in on that. The next set of questions, there's a theme, I think, developing, and it's one I'm interested in as well, and it's about trust. So something that I have been thinking a lot about is declining trust in mainstream media and public institutions. And, there are absolutely reasons that members of the public might be skeptical, I think, of academics. There has historically been like institutionalized racism, or, in the academy has historically left out marginalized voices in scientific inquiry. Or you might point to scientific histories of eugenics, right, which is obviously a pseudoscience, but was accepted enough to cause a lot of damage. P-hacking, is a contemporary phenomenon that's eroded trust. So given that very real crisis in public trust, how do scientists work to build trust in the public eye? What's the role of the researcher, the disciplines, academia, in building that trust, do you all think? Thanks, John.
I just want to push back at the premise. there are problems in particular sciences. The replication crisis is a crisis that has been peculiar, I think, to psychology and certain social sciences. The difficulties of things like eugenics, again, they pop up in certain particular cases, but there's vast amounts of science that simply don't have the problem. I gave the example of the periodic table of the elements. I mean, chemistry has been pretty stable for 200 years. There's no reason not to trust, chemists. And you can go through science after science after science, and you have every reason to trust them. I'm concerned that we spend so much time giving prominence to the cases where you shouldn't trust the science. And so people just get the impression that, oh, science is all terribly untrustworthy. I think it's, I suppose, what a statistician would call a sampling fallacy, right? If you sample all the bad cases, you think that's all there is. And I wish we'd stop doing it.
Well, I'll just jump in and say that to the extent that it is true, if there is truth to the mistrust of science, I think that scientists have an opportunity to be the embodiment of a trustworthy individual. And I think that a couple ways we can achieve that are, the way that we communicate the science, the way that we talk about it, the language that we use, rather than coming across very arrogantly, like I have proven something and it's too obscure for you to really understand. Just taking a humbler view, and saying, well, these are my results. This is why I think this. When you're communicating things, I think goes a long way. And I think for me, I've noticed too that, when I'm standing up in front of the classroom, and as a scientist, I'm standing there as a model of a scientist, that I like to, sort of show that I am a human being too, that I'm not this sort of cold, calculating person stereotype that people think about. I often will bring up things about a previous career in music, or things that convey my sports interests, that, I am a well-rounded package. I'm not the insufferable nerd that you see in The Big Bang Theory. And I do that deliberately to kind of push back against those stereotypes, that I am a relatable person. I'm just like you. And, we're not up in our obscure ivory tower talking down to you.
Thank you.
I guess, can I jump in here?
Yep.
Please? It's a tough problem. First of all, I'm very sympathetic to what John was saying, but I'm going to focus on the parts where people have been attacking it, or where faith has been eroding. And I don't know the answer, but it feels like a lot of the erosion of trust is by design. It's people who don't like the message of such and such a field, let's pick climate science, and they attack it. And the way you attack it is the way, well, we've seen it in the last few days, right? You attack this journalist as being this unreliable guy. It doesn't matter that the reliability of the journalist has anything to do with the chat GPT leak, or the signal leak. And this is a historical thing. People attack science that they don't like. And of course, that erodes the trust in that science. Rachel Carson is what comes to mind. She was attacked when she wrote her book, her famous book about ecology. So now the question is, how do you counter political attacks on a given field of science? And that's hard to answer, because I think the way you do it is by counterattacking like politicians do. And we're not politicians, and we shouldn't be politicians. So that leaves us in this uncomfortable place of just standing in the boxing ring getting punched in the face. And it's just like, okay, punch me. I'm a scientist. I can't punch back. Go ahead, punch me some more. And there's little you can do. Right now I am struggling trying to think what could you do to counter this kind of thing, and nothing is particularly coming to mind. Maybe I'm being too pessimistic. I'll throw it back to the other panelists.
I'll just add, I unfortunately don't have something optimistic to share. It's interesting. It reminds me of a book I remember written about 15 years ago called Don't Be Such a Scientist, Stupid. That was sort of about saying that the reason scientists fail to connect is because they're nerdy and technical and they have a certain way and they just can't connect with other scientists. So it was a whole book with the public. So it was a whole book about, how to like make yourself more approachable, how to make arguments more accessible. And you think about in my field, when I first was studying to get my PhD in the early 2000s, there was very little focus on science communication. But as the field developed, this huge growth in science communication, and people were even being encouraged to not only write their dissertation, but to also make a video where you sang about your dissertation in like a 5-minute clever way, and just all this sort of creative ways of trying to break it down and make it approachable. But as I'm thinking about that, like I want to say that's had a positive effect on the public's relationship to science. But I don't know that I can, because it's kind of going at the same time that there's also been what feels like, and I think there's evidence for of a declining trust in expertise, including science. And so I'm a little flummoxed as well about how to work on this issue.
I'm gonna keep you actually in the spotlight here because there's a question for you, which is, I think, kind of a follow-up. So like, when you encounter climate change skepticism in your job, like, are there any tactics that you've found effective at impacting people's views?
Yeah, so the kind of best approach that I've been learning is, and that's kind of, there's a lot of psychological work to support this, a lot of communication work, is really about this idea that you kind of need to start a conversation with a person, and that the best way to do that is to allow them to first sort of express their point of view and where they're coming from, and for you to listen to that, to be receptive and open to listening to what they have to say. And then kind of once you've shown that you've listened, you've acknowledged kind of what they're saying, to then move into offering your point of view and your evidence and your counterpoint of view. And so it becomes a dialogue, right? And that allows that person to be seen and heard first, which I think might allow them to be open and receptive to what you have to say and what you're sharing. It's I it's still hard. Like, that's the theory that I try to bring and I work on with some of my education colleagues. We do work where we go out into communities and we open up conversations. Like, we'll do sort of polling. We'll ask people, like, are you concerned about climate change? And let them vote and tell us if they're concerned or not concerned. And then we'll say, why did you vote that way? Tell me about what you're thinking, and open up a conversation. And I will say that I'm able to find to have complex conversations with people, and I learn a lot about where their skepticism is coming from, and that isn't what I would have assumed, right? So I learn a lot more about the complex thinking that people bring to these topics. And but it is hard. I haven't found a way to really hit them with the science. I don't know, there's only so far you can get where you sort of share what you know and you have a good conversation. And that, I think, is the best you can sort of do, is then they had a positive interaction with you and they felt heard, and that might make them more receptive in their next moment. You didn't fight them. You didn't make them get stressed. You created a comfortable experience. And I think that that helps.
Yeah. So interestingly, you don't present them with a whole bunch of evidence. You actually engage on kind of a human level. Interesting.
Because
Um,
evidence can be just really overwhelming, and I think people get intimidated and they have already defenses they've often built up against these things. So I mean, so I think, and a lot of it has to do with politics too, right? And that you quickly realize that it isn't about the science. They're actually concerned about our economic situation, or they're concerned about China's emissions, you know, and so pretty quickly you get into a different dialogue and you realize that you can sort of accept the science, but like, what are we going to do about it? And that's maybe where we need to be having the conversation anyway. So, yeah.
yeah, I mean, there's a follow-up question, which I think everybody can chime in on here, which is, why do you think some pseudoscientific claims have so much staying power? The anti-vax movement especially comes to mind. Thank you, John.
Um, I'll confess to a certain amount of pessimism here. Perhaps I could just talk about my own area. I do a lot of Einstein stuff, and so I'm the beneficiary of all sorts of people who want to prove Einstein wrong. I find amongst people who have conspiratorial thinking that it is something that is very satisfying to them. The idea that they know things that other people don't know, they know things that the mainstream says this and everyone believes it, but I know better. I found the secret. So by the time I'm talking to a really set in his ways Einstein denier, it's too late. They're too invested in the idea that they know more. And I expect similar things are happening. I don't know as much about the psychology of climate change deniers, but I expect a similar things happening there. The short answer is, by the time the zealot is approaching you, it's too late. You're not going to be able to move them. They're too committed to their ideas. The people we need to get to are the ones who haven't made up their minds yet. And I'm encouraged because I run into so many students who haven't made up their minds yet. And if you just go through the material with them, they see the sense of it. But, I don't know if that matches other people's experience. I take it we all see different slices of resistance movements.
I would echo what you said, that I think that the staying power does come down to some appeal that a belief in these pseudoscientific claims or conspiracy theories has, and it is deeply satisfying for many people. And I also think that this is also the double-edged sword of living in the information age, is that the staying power also gets perpetuated by the fact that if I Google, yes, I could get ChatGPT's answer, but if I have some echo chamber that I'm a part of that thinks otherwise, and I continue tweaking the words I use in my Google search, I can try to find something to confirm. That's where that confirmation bias comes back in, to confirm what I think supports these ideas, and that information or misinformation is still out there, and it's still accessible to me, and perhaps even more so in the information age, because I can just keep searching. I don't have to, like you were pointing out earlier, John, you'd have to have gone to the library. There's a flip side of that too, right?
I agree with everything I think that's been said. I have actually some experience with this, like Nicole does. I consult for the telecoms industry, trying to fight against misinformation about cell phones and radio towers and things like that. And my experience is very similar to what you were describing. People come to, you can ask yourself, why do you believe what you believe? And there are a whole bunch of things that come in to set up your personal beliefs, where your information comes from, who you choose to trust, your history, your education, your religion, your politics, all of this comes in and feeds what you believe. I agree with John. I think there's a level of psychological comfort that people have when they take on one of these beliefs. It makes them a little different from everyone else. They're kind of rejecting the norm in some slice of reality. And strangely enough, even by rejecting the masses, they become part of a community. And they like their little community, their community of flat earthers or anti-vaxxers or whatever it is. It gives them a sense of comfort. I think that really helps these things survive. There was another point that Nicole, both of you said that it's very hard to dissuade people from these. And I've also found that. It's the people at the margins that people like us have most effect on. So I agree with both of you on that.
Okay. Well, I actually think this might be a good moment to wrap things up. And again, thank the wonderful panelists for your presentations and fruitful discussion. I'm going to hand it back over to Satish, who has a thing or two to say to finish.
Yeah. First, let me second what you just said, Elise, and thank the panelists for a marvelous, even if it was a bit sobering kind of discussion, especially at a time when the attacks on science are so intense. It's nice to hear some of the ideas. For example, what Nicole was saying about communication with people. I will end by also thanking John Rubin of the Math Department. He and I have been partners in organizing this series since it began back in 2021. And usually he's the one who does all the introduction, does the welcoming. Today he came in a little bit late because he was teaching, so I substituted. I think that's it. Thank you so much. Again, this was really wonderful. And good night.
Thanks, everyone.